Hello student, my name is Shashank Shekhar. So we have started the chapter coordination compound and we have done two lectures on it. In first, we have seen the Warner's theory, and in second, we have seen what is say our coordination sphere and what are the terminologies that is related to a coordination entity. So we have seen there in the Warner theory. So the most important thing in the Warner theory was about the valency. Metal can have two types of valency in a complex. First is primary valency, and second is secondary valency. If I talk about in the second class, we have seen first of all the difference between double salts and complexes. So both double salts and complexes are formed by the reaction of two compounds. But the difference between them is that if you dissolve your double salt into water, then that double salt is completely dissociated inside the water, whereas the complexes do not completely dissociate in water. After that, we have moved to what is coordination sphere. So the entities that are present inside the bracket in the formula mass. So we will see how we write the formula mass. That is a later on topic to discussion. So once you are with the formula mass, so the entity that is present inside the formula mass is termed as in coordination sphere. And in coordination sphere, we will have central metal ion and we will have ligands. Now ligands can be of three types: neutral, anionic, and cationic. In neutral, we can have ammonia, water. In anionic, we can have OH minus or Cn minus. Clear? While in cationic, we can have NH2 plus. Okay. So this were the classification of ligand. Further, we can classify them on the basis of their denticity, means the number of donor atoms that can donate simultaneously. So for that, we have seen three types. Although we have seen four types, that is monodentate, bidentate, and then tridentate and hexadentate. For monodentate, we can have water, we can have ammonia, we can have chlorine, OH minus. All these are monodentate. For bidentate, we can have ethylene diamine, okay, or we can have oxalato. In tetradentate, we will have say the example of hexamethylene diamine. Sorry, ethylene diamine tetraacetate. So this was example of hexadentate. For tridentate, we can have this example, that is NH2, CH2, NH2, CH2, NH2. So it can donate from these three sides. So it is tridentate, right? So also we have seen the way of calculation of the oxidation number, which is being represented in bracket form in the parenthesis. We will see that also when we will try to write the formula mass. Now let us move to our today's topic. So the today's topic are, first of all, the nomenclature. Second, the formulas of mononuclear coordination entities. What is the meaning of mononuclear? Means only one central atom is present. We will see the naming of this mononuclear and their examples. So nomenclature of coordination compound is the most important, and there is a certain specific systematic way of writing the coordination name of this coordination compounds according to the nomenclature, and they are all based on this IUPAC, that is International Union of Pure and Applied Chemistry. So let us start with the formula first. How we'll write the formula? So for a mononuclear compound, there are multiple entities. First of all, it has a central single atom. So the central atom is listed first. Then we have ligand that are listed in the alphabetic order. Now the placement of a ligand in the list does not depend upon its charge. So this should be clear. It is dependent upon alphabetic order. For polydentate ligand, also alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used. So abbreviated like our ethylene diamine, which is abbreviated as EN, or our ethylene diamine tetraacetate, which is ADTA, which has an abbreviation form as ADTA. So in case of abbreviation, we will take the first word, say E and E in this case, right? Then the formula of the entire entity, whether charged or not, is enclosed in a square bracket. What is the meaning of this? That after writing the whole formula, we keep it in a square bracket. And ligand abbreviation are also enclosed in parentheses. So if you have an abbreviation, say we have EDTA, then we will placed it in a parenthesis. We will not have to write the charge of ligand. So this should be kept in mind that we do not have to write the charge on it. There should be no space between the ligand and the metal within a coordination sphere. So you will never write it as in this way. There should be there should be no space. It should be written in this way, NiCO4. Okay. So when the formula of a charge coordination entity is to be written, without that of the counter ion, the charge is indicated outside the square bracket. So we can have the counter ions, we can have 3Cl minus. If the counter ion is not present, we have to represent the charge. If not, we do not have to represent the charge. So for example, so first what we have done, first we have written the central atom. Then we have ligand. The ligand in the alphabetic order. Here only one ligand is present. It is homoleptic coordination compound. So we do not have any confusion for that. Similarly, the second example also has only one type of ligand. So it is also a homoleptic coordination compound, and the central atom is written first. Now the charge, overall charge, is written as the superscript. Now this charge will be balanced by any counter ion. So here we can put 3Cl3. Here we can put K3 for balancing both of this charge. Now if I talk about the naming, it is written in this way. So the cation is named first in both positively and negatively charged entities. We have seen the example of positively and negatively. We can have both charged entities. Now the ligands are named in the alphabetic order. Again, the name is also written in the alphabetic order. This procedure is reversed for writing formula. So the ligands are named in the alphabetic order before the name of the central atom. So you must have seen that in writing the formula, we first write the symbol of the metal, then we write the symbol of the ligands. But in this case, we write first of all the ligand name, and then we write the central atom name. Now name of the anionic ligand ends with O. How? If we have and those of neutral and cationic ligand are same except H2O, which has aqua, amine, which has NH3, and carbonyl, which has CO, and nitrosyl, which has NO. So what is the meaning this O? Suppose we have Cl minus, then we will not write it as chloride. Instead, so we will not write it as chloride. Instead, we will write it as chlorido. That is, this O here will be added. Similarly, nitrito. Okay. Or we can have, say, cyano. Now, prefixes mono, di, tri, etc. are used to indicate the number of individual ligand. So we can have, say, 3 ammonia, so there will be triamine. We can have 4 aqua, so hexaaqua. And when the name of the ligand includes a numerical prefix, then we use this term bis, tris, tetrakis. So this is the most important thing. So hexamethylene diamine. Suppose this is a ligand. Now this already consists of hexa. Now suppose 2 of such entity are present, then we will not write it dihexa. Okay, we will write it as bis is for 2, so we'll write bis hexa and the rest of the name. Clear? So for bis is for 2, tris is for 3, and tetrakis is for 4. Did you get my point? So the ligand which has already such prefix such as hexa, mono, di, tri. So for that we will not use this bis di, tri. We will use this bis, tris, and tetrakis. You can have all many examples, such as, say, we can have the example of ethylene diamine. Okay, ethylene diamine tetraacetate, ADTA, or we can have the example of ethylene diamine only. So for that we will not use this thing. Here we know that this is its name is triphenyl phosphine. So this is triphenyl phosphine. So it already have a tri in the starting. So for that, since there are two such triphenyl phosphine present, so we'll write it as bis. Then inside the bracket we'll write triphenyl phosphine. Now, since C comes first, so we first write the chlorine, that is dichlorido. See, this O represent that it is an anionic ligand. At last, we will write the name of the metal along with the oxidation state in the parenthesis. So same thing written here. The oxidation state of the metal in cation, anion or neutral ligand is indicated by the Roman numeral in the parenthesis. If the complex is a cation, the metal is named as the element. No problem. So for example, CO in complex cation is called cobalt, platinum is Pt is called platinum. If the complex is anion, the name of the metal ends with 8. So here we can see that overall this complex has a charge of minus. So therefore we will write it as cobaltate. Okay, clear? For writing iron, we will not use this iron. Instead, we will use this ferrate or ferrous. So what will be the name of this? So 4 are present. So tetra. What is the name of this ligand? It is thiocyanito. Thiocyanito. Tetra thiocyanito. Cobaltate. What is the oxidation number here? So 4 are present. So if you try to calculate the oxidation number for this, CO SCN 4 whole 2 minus. So if we consider this as 4, SCN is a charge of -1, that is equals to 2 minus. So X would be +2. Okay. So cobaltate 2. So we will write it here. CO SCN whole 4 2 minus. Therefore, we will write first of all the name of the ligand, that is tetra for 4, tetra thiocyanate cobaltate 2. Each of these things should be mentioned. O for negatively charged, 8 since the complex is overall negatively charged, and 2 is the oxidation state. Clear? Next is the neutral complex is named similar to that of the complex cation. So if it is neutral, say we can have the example of NiCO whole 4. Overall, it has a charge of 0. So this is carbonyl. This is CO. Okay. So first we will write the name of the ligand ending with nickel with a 0 oxidation state. Clear? Here will be the name of the ligand. So let us see some examples. So first of all, we have the example of chromium NH3 whole thrice H2O whole thrice. So it is a heterolytic complex. Heterolytic complex, why? Because it has two types of ligand. First is ammonia, second is water. So how we'll name it? First of all, we'll write the name of the ligand in alphabetic order. See, when you are writing di-tri, you will not consider the alphabetic order according to D of di or T of tri. You have to see the actual name, right? So for ammonia, this is ammonia. Okay, so we'll name it as amine, not ammonia. Okay, this will be named as amine, and this water will be named as aqua. Yeah. So who comes first? So both has a A. We will move to the next letter. It is M. KLMNO So amine come first. So first we'll write amine. How many amines are there? 3 amines. So triamine. Then we have aqua. How many aqua? 3 aqua. So triaqua. First we have written the name of the ligands, then the name of the metal ion. So what is the overall charge on this metal ion? We'll see it. Since they are neutral molecules, we do not have to worry about adding O after their name. So we will see the oxidation is overall charge on this complex. So ammonia has a charge of 0. It is also has a charge of 0. But there are 3 chlorine atoms present outside this entity. Means they all have 1 negative charge, so 3 negative charge, but it is neutral overall. Therefore, this entity must have a charge of +3. So we do not have to add ATE after chromium. You do not have to write it as chromate. Therefore, triamine, triaqua, chromine, chromium, oxidation state of chromium, how we will calculate? So overall the complex is neutral. Let us assume 3 is the X is the charge on chromium. There are 3 amine with 0 charge, and there are 3 water with 0 charge. The counter ion is chlorine. We are adding this also. There are 3 chlorines with -1, and the overall complex is 0. Therefore, it will be 0. So this will be 0, this will be 0, that will be equals to +3. Therefore, we have written 3 in Roman numerals. At last we have chloride, so we have written chloride. See students, we do not have to mention this 3 in this chloride name. Okay, so this can be calculated once we are given the name of the complex entity. So the same thing is written here, that the complex ion is inside the square bracket, which is a cation. The amine ligands are named before the aqua ligand according to alphabetic order. So there are 3 chloride ion in the compound. Therefore, the charge on the complex might be +3. But from the charge of the complex and the charge on the ligand, we can calculate the oxidation state. In this example, we have all the ligands neutral. Therefore, the oxidation number of chromium is also +3. Next is this example. We have cobalt ethylene diamine. Okay, we call it as ethylene diamine EN also. It can be abbreviated as EN also, or we can write the IUPAC name, that is ethane 1,2-diamine. So we'll write both of this and we'll see how both of this are written. First of all, this ligand is neutral, okay, and there is a negatively charged species outside it. Clear? So this entity should be positively charged, but there are 2 of them. So 2 of each of them. So let us write it. First of all, find the oxidation state. So there are 2 cobalt. So if one has oxidation state of 2, 2 will have oxidation state of 2x. Now ethylene diamine, that is En, is having a charge of 0. So 2 into 0 plus sulfate has a charge of 2. Clear? Sulfate has a charge of 2 minus, and there are 3 sulfates. So 2 into -3. That would give us 0, because the charge on the complex is 0. So if we calculate it, it would be -6/2, or sorry, +6/2. That would give us +3. Therefore, the oxidation state of cobalt is +3. What will be the name of this? So we have seen the complex, the ligand looks like this. We have 2 CH2 and NH2 on both sides. If you write the IUPAC nomenclature, then 2 carbons, so therefore ethane. And at first and second carbon, we have 2 amine groups. So 1,2-diamine. Now this already has a di in it, so we cannot use this. Since 2 of such are present, we cannot use, let's say, it will be 6. Okay, so we cannot use this di tri again as prefix. Therefore, we have to use bis and tris. So there are 3 such present. So we'll write tris, and the metal ion that is present is cobalt. Cobalt has a oxidation state of +3. Then we have sulfate at last. Clear? So this is the name of this. The same thing written here. The sulfate is the counter ion in this molecule. Therefore, it will take 3 sulfates to bond with 2 complexes of ion, and the charge on each complex will be +3. We have seen that. Further, ethylene diamine is a neutral molecule, so the oxidation state of cobalt in the complex will be equal to how much? +3. That is the overall charge on the complex. Now we have to indicate the number of cations and anion in the name of the ionic compound. Now, if I tell you how you will name this compound, How you will name it? See, first of all, both of this is say neutral molecule. Okay, and what about this? This is not neutral. This ligand is not neutral. It is at a charge of -2. Clear? Now, next thing, there are three such presents. So if you assume, so we are assuming that both of the silver are having the same oxidation state. There can be a chance that both of will contain different oxidation state, but here this complex has, so you should remember this complex, that in this complex both of the silver atom have same charge. How I will calculate the oxidation state? So there are 3 Ag and 3 into 2, 6 NH3. So let us assume that X is the oxidation state of ammonia, plus ammonia has a, sorry, of silver. Ammonia has a charge of 0. 6 ammonias are there. Now again here one silver is present and 2 CNs are present, so -2. That is 1 into minus 2, minus 1 into 2, and the overall charge on this coordination compound is 0. Clear? 3x plus x, that is 4x, and that is equals to -2, right? Clear? That is equals to -2. That would give us an oxidation state of 1/2. Okay, I think something is wrong here, so we'll see this example in the next class. Okay, so leave it for now. So other than the oxidation state, we can write the remaining one. First, we will name this compound. So in this case of compound, in these compounds where we have two entity, we will name it in the order from left to right. So first we will name this. So two amine are present, so diamine. Silver has oxidation state of 1. Then we have this entity in which we have only one ligand, that is cyano. So dicyano, O for the negative charge on the cyanide. And since this is a negative complex overall, therefore we have written argentate. See, when the molecule is neutral, when the overall entity is neutral, we have to write only the name. So we have written silver, no problem. But where we have to write the, say, our this name, that is negative complex name, because this complex is negative, we have to write argentate. So we cannot write it silverate. Okay, we will write it argentate. Similarly, for if it is simple iron, either it is positively charged or neutral, then you write iron with the oxidation state outside it. If it is not so, if it is negatively charged, then we have to write not ironate but ferrate. So these two things should be remembered. Clear? Now next, let us see an example here. So we have an example, that is K for FeCN6. Now let us try to name it. So first of all, the counter ion is 4 K plus. Therefore, inside this complex, this is negatively charged. This FeCN6 overall has a negative charge because the counter ion is positive, and that has a charge of 4 minus. The anionic complex is this. What is the ligand? It is Cn minus. So we will, and 6 Cl 6 cyanide are present. So hexa cyanido, right? Then central atom is Fe, but since it is negatively charged, we will not write it as iron, but we will write it as ferrate. If you try to calculate the oxidation number, so overall it has a charge of 4 minus, so x plus 6 into -1, that would give us a oxidation state of +2. So what would be the name? First, the name of this, say K4 will be written. So this is also an important point. So when we have a positive counter ion, so it is written before the coordination complex, and in the nomenclature also name comes first. So first we have written potassium, then we have written the name of the ligand, that is Cn, that is cyanido. Okay, then we have written ferrate, which has oxidation state of +2. Clear? So this is a very good example, and you should remember some of the things. I would say you should remember some of the things. So what are those things? If the coordination is fair, if the coordination sphere is negatively charged, then metal ion name ends with ate as the suffix. But two are the exceptions. We will not write it directly, right? For argentate, that is for silver, and ferrate, that is for iron. So we have just used the Latin name rather than the normal name. Second thing, if di tri is already present in the name of ligand, then we will use bis, tris, or tetrakis. Okay, this is the important point. And one more important point, I would say, negatively charged ligand ends with name O, like cyanido, chlorido, or oxalato. Okay, and the last point, I would say that in case of positively charged counter ion, its name should be written first. So we have seen an example of this. So these 4 points are the case of exception. So you should remember these 4 points. The remaining points are easy to remember, but these are some exception cases. Clear? So with this, I end my lecture. Thank you.